So in the last video, we were looking at different concentration units, and now we're going to look at, while still considering some of those concentration units, we're going to start looking at colligative properties. These are going to be properties of solutions that are going to be dependent on essentially how much, in terms of the number of particles that are dissolved, rather than exactly what that substance is that's dissolved. And we're going to see with each of the four examples here kind of what's going on in each of those processes. So the vapor pressure of a solution is going to decrease relative to the pure solvent. The boiling point is going to increase. The melting point will decrease. And then we'll see, and actually this is typically called freezing point depression. And then we'll see what osmotic pressure is as well. But with the vapor pressure, if we just think about what vapor pressure is for a second, we can look at the image on the left here. We're going to essentially have some closed container. So we got a beaker with a lid on top of that pure solvent. And then at equilibrium, we're going to have some amount of that substance in the gas phase. And then we'll have the transition between both of these phases now occurring at an equal rate. And then just remember, with the weaker the intermolecular force, the easier it is to separate these molecules from the liquid phase, the more of it we'll just have in the gas phase, so the larger the vapor pressure is as the intermolecular forces decrease. But what we're going to see with a solution is, now that we've got the solvent dissolved, we can kind of think, or not the solvent dissolved, now we get the solute dissolved. We can kind of think of that as sort of anchor points, because initially we're going to have just the intermolecular forces of whatever this solvent is kind of holding it together. But now we're going to have the intermolecular forces from the solvent as well as the intermolecular forces from the solute. So you can kind of think of those as almost anchoring that solution down, because we're just going to see the vapor pressure is going to decrease. We're going to get less of this substance in the gas phase. And that's why just in this image, there's smaller arrows for the solution than there is for the pure solvent. And with this, we've got an equation we can use to specifically calculate how that vapor pressure is going to change. So PA on the right-hand side, where we've got that little degree symbol, is going to represent the normal vapor pressure of that pure solvent. X is going to be the mole fraction. And then for this one, just recognize this is going to be the case where we're actually looking at the solvent. So when we're looking at mole fraction, typically we have a small number on the top divided by the total moles of solution. But in this case, since we're going to be focused on the solvent, the top number is typically going to be pretty close to whatever that total number is, because for the most part with solutions, we're going to have a lot of that solvent, which is a little bit of the solute. And then PA on the left is just going to be the vapor pressure of that solution then. So we've got pure vapor pressure on the right times that mole fraction. And then since the mole fraction itself always has to be between 0 and 1, we're always going to see the vapor pressure of that component in a solution is going to, or the solvent, we're going to see is less than the pure vapor pressure. And then with these different properties, we'll see afterward, we kind of look through all of them, they'll be different practice problems we kind of go through. But if we think about the vapor pressure, the temperature at which that vapor pressure is equal to atmospheric pressure is just the boiling point. And if we're seeing the vapor pressure decrease, we're essentially taking this boiling point line and moving it to an even further temperature. So what we're going to see with the boiling point is the solution is going to undergo what's known as boiling point elevation. So we're going to see the boiling point is going to increase. We're just representing that here with delta TB, so the change in the boiling point. And again, we can see that's going to be a positive increase from a pure solvent to a solution. And then with the freezing point, we see just the opposite. So that's why we're calling this freezing point depression. We actually see this one decrease. And with this, with the freezing point depression, this one is most commonly observed just during the winter time. If it's expected to be very cold and there's moisture on the roads, they often salt the roads in order to then make a solution. And then we see the freezing point of that water as a solution decreases. So now it's got to get even colder in order for that road to freeze over. Just makes it a little bit safer in terms of driving. Of course, there are some negative consequences environmentally from the use of salt on roads, particularly if it then runs off into waterways. But in terms of the transportation, it definitely does make it a safer trip. And then with this, just to go back to kind of think about this actually, with the freezing point and the boiling point changes, the boiling point is going to be kind of the same idea as this vapor pressure. Now we've just got essentially increased intermolecular forces, so we're just holding on to those molecules more. So it's just going to take more energy. It's going to take a higher temperature in order to separate them out. And then the way I like to think about the freezing point depression is we typically see, again, water is going to be kind of a weird case because it does expand as you freeze it. That's why ice is less dense than the liquid. That's why it floats. But with the liquid to solid state, we're going to see these atoms are typically going to get closer together. We're going to have a more rigid arrangement, more fixed sort of interaction between those different particles. So when we've got a solution now, we've got kind of these pieces that are going to kind of disrupt that crystal. So we're going to need to get it to an even lower temperature to kind of have that solid form. Whereas with the boiling point, now those solute molecules are just going to kind of hold on to the solvent better. And so we're going to see less of it get into the gas phase in terms of vapor pressure. So we're going to see a higher temperature being needed in order to actually boil that substance. And then in terms of actually calculating exactly what those new boiling and freezing points are, we've got two very similar equations. So in this case, we're looking at the boiling point elevation. So how much is that boiling point going to increase? Note that we're looking at delta T. So this is just telling us how much it's going to go up. It doesn't actually tell us what the new temperature is. We would need to know what the actual boiling point is. And then that change in temperature is going to be equal to a constant. So KB, if we look at it, degrees Celsius per molal. And then with it, that constant is going to be specific to the solvent itself. So we can see water, we've got a nonpolar solvent in benzene, ethanol kind of in the middle, carbon tetrachloride, also nonpolar, and then chloroform. But we can see each of those is a different boiling point constant. The molal boiling point elevation constant to be specific. And then with the freezing point, it's the exact same formula. It's just in this case, we've got a different constant here. So just note that the boiling point and freezing point constants have different values. And then if you look at them, you'll notice that all of the freezing point values are larger than the corresponding boiling point constants. So what we're going to see is when we make a solution, the freezing point is going to decrease more than the boiling point is going to elevate. And then again, just with the M here, that's representing molal. So we're going to have moles of solute over kilograms of solvent. Let's see the same equation. We just want to note with the freezing point, since it's freezing point depression, this is going to be a negative. So sometimes we actually just have negative Kf times M, just to recognize that this temperature is going to decrease from the original freezing point. And then with this, we're going to have kind of one other piece because the molality doesn't actually tell us how many particles we have there. So if we think about an electrolyte, so something like an ionic substance, something like sodium chloride, we're going to get 2 particles for every molecule because we've got a positive sodium ion, we've got a negative chloride ion. And then we can see the water molecules themselves are just going to hydrate those. So we've got the negative oxygen around this positive ion. We've got the positive hydrogen around this negative ion. And then if we think about something like ethanol, so you can see here, and then we've got the water molecules in the back. With ethanol, since it's covalent, it's not going to split apart into separate ions. So unlike the sodium chloride, which gives us 2 particles per molecule, in this case, we're just going to have a single one. So even if we had the same molality of these solutions, since we have 2 particles here, we're going to see the sodium chloride would more impact the freezing point and the boiling point temperatures for that solution. But with it, it's not going to be as we see here, it's not going to be a perfect change. So it's not going to be twice as large for the sodium chloride. And what we're going to see is that's going to be due to the Van Hoff factor. So with this, if we think about sodium chloride again, we're going to have those two ions making up the molecule. But when we actually have a solution, if we kind of took a snapshot of that solution at any given second, we may have those ions separate. But because we've got the opposite charges here, those are going to draw them together. So for a split second, we may actually have the molecule kind of reform. So we're not necessarily going to have exactly two ions for every molecule. It's going to be a little bit less than that. And that's what we're going to use the Van Hoff factor to kind of represent. Again, reassociation for a short time, meaning that we're going to have these ions be drawn back together for a little bit, and then we'll have them re-separate into solution. So when we're looking at the Van Hoff factor, you can see here we've got 4 different substances. So sucrose is going to be covalent, and then ionic for these other 3. So with the sucrose, we can see the limiting value is going to be 1. And then we see that same thing for all of the different concentrations here. So 0.1, 0.01, 0.001. Because with the covalent substance, since they're not going to dissociate, we're always going to have exactly that many particles. But whereas the ionic ones, we actually have those different ions that are going to break apart. We can see the limiting value is going to be 2 or 3, depending on sodium chloride and magnesium sulfate. Just have one cation, one anion. But the potassium sulfate now has 2 potassium to balance out that -2 sulfate. So we've got 3 ions there. That's why we've got the limiting value of 3. But then with these different concentrations, we can see what that what it's really going to act like, because again, we're going to have some reassociation of these substances. So we're not always going to have 2 for the sodium chloride or the magnesium sulfate. We're not going to have 3 ions per molecule or 3 particles per molecule, I should say, for the potassium sulfate. And we can see as the concentration decreases, though, we start to approach that value more. So with the sodium chloride, 1.87 with the 0.1 molal solution. But then as we decrease it to 0.01 or 0.001, we see that number start to approach 2. And then we see the same trend with these other substances. But with it, the reason we're going to see that these values are different is going to be partially due to the charge here. So if we think about magnesium sulfate versus sodium chloride, both of them having a limiting value of 2, but the magnesium sulfate's much lower. It's going to be because the magnesium sulfate's +2 and -2 in terms of the charge on those ions, whereas sodium chloride's just +1 and -1. So the magnesium and the sulfate are going to have more of an attraction to one another since they've got those larger charges. So we're going to see those are going to be drawn together more. And that's why we've just got a lower value for these this solution than we do for the sodium chloride. There's going to be more of an attraction between that magnesium and the sulfate, so we're going to have that reassociate more often. And then with the potassium sulfate, you can kind of think about the same thing. We've got a -2 sulfate, but now we've also got 2 potassium ions. So it's kind of got more of an opportunity to reel those in. And that's why, again, we see a bigger decrease from the limiting value than we did with the sodium chloride itself. So when we're looking at actually using the delta TF or the delta TB would be the same idea. So the freezing point elevation calculation or the boiling point or freezing point depression or boiling point elevation, excuse me. We're just going to have the Van Hoff factor as kind of the extra piece there. If it's a covalent substance, we don't really need to include it since it's just going to be 1 across the board. But if we had an ionic substance, we would want to make sure we include that Van Hoff factor just to accurately represent how many of those particles we're going to have. Okay. And then with osmosis, so we're going to see osmotic pressure, but with osmosis, just first, what this is going to be is the transport essentially of just water across some membrane, essentially to kind of balance out the concentration. So with diffusion, we're thinking about kind of, if you think about a solution, you make a solution, you throw some salt in a cup. Initially, it's going to be in one area, but then it's going to be able to diffuse through the rest of that solution. And it does that so that the concentration is even throughout. We're going to see osmosis is kind of that same idea where we're going to have a movement in order to balance out the concentration, basically. But in this case, rather than having the solute move, we're going to have the solvent. So we're going to have that water actually move. So if we look at the picture here, we can see we've got two different solutions, and then the semi-permeable membrane is just going to be something that allows certain things to pass through, but not others. So in this case, we're going to allow the movement of water, but not the solute. So initially, we've got a high concentration solution on the left, low concentration solution on the right. And what we're going to see is the solvent, so in this case, the water, is going to move from higher concentration to lower. And if we think about it, the concentration here is in terms of the solute itself. So in a dilute solution, we're going to have a higher solvent concentration. And that's why throughout this picture, we see the water move from the right to the left, because in this case, we've got a higher solvent concentration on the right. So it's going to move to the left in order to actually kind of balance it out. Because if you think about it, if we've got lower solvent concentration on the left, moving that direction will balance out the solvent concentration. Or even if we think about it from the solute perspective, initially we've got less concentration for that solute here on the right. So now if we remove water, we're still going to have the same amount of solute, but now we're going to have less solvent on that side. So we're going to see the concentration is just going to increase in that way. And it's also going to decrease the concentration of that solute on the left, because now we're going to be diluting it with more water. And then with it, you can also kind of see the next piece that we're going to be looking at, the osmotic pressure. So we can put some force on this side, and then the force needed to prevent that solvent from actually moving across this semi-permeable membrane is just going to be known as the osmotic pressure. And we're going to use a pi symbol just to represent that. So the osmotic pressure is going to be equal to moles over volume, so just molarity, times the gas constant, times the temperature in Kelvin. And then the gas constant we're going to be using is going to be 0.08206 liter atmospheres per mole Kelvin. And then just to think about osmosis for a second, if we think about red blood cells, this is going to be important because we can either have water move in or out of those cells depending on the type of solution they're in. So if we think about an IV when we're using some sort of IV to supplement fluids for a person, if the concentration of that solution that we're using doesn't really match the blood, we're going to see water either move out or into those cells, and either way that can cause a problem. So if we think about it in this case, we've got a high solute solution, high solute concentration solution outside of the blood cell, meaning we've got a lower concentration on the inside. That means we've got extra, kind of thinking about the concentration, we've got higher concentration of water inside the cell. So we're going to see that water move through the membrane of the cell into the solution on the outside. And that's going to be known as crenation. So essentially the cell kind of shrivels up and basically just sort of dies in that case because it's no longer going to have the water it needs. And then in the opposite, we kind of see the reverse case. Excuse me, sorry. We see the reverse case where low solute concentration, meaning we've got a lot of water on the outside, and that's why we're having it move into the cell. And whereas in the previous one, we see that the cell kind of shrivel up and die. In this case, we're going to see the reverse happen where it kind of expands so much that it can eventually just burst. And again, like I was saying with the IV, if the solution that we're injecting doesn't match the blood itself. Either of these processes can occur depending on what the solution is. And then either of them are going to be problematic for the person that's then receiving that IV. So when we're looking at those IV fluids, they need to be isotonic, meaning that the solution itself matches the blood so that we don't have, in the case of hypotonic, like we see here, the cell bursting, or in hypertonic, like we saw in the previous one here, the cell shriveling up and down. And then with these ones, just thinking about osmosis quick, just a few other examples. So sometimes if you eat a bunch of salty food, you wind up retaining water, so you can wind up bloating. It's going to be because of this reason. The salt, you can kind of think of it as staying in the cells. So then the water is going to move in that direction. So you just retain water. And then with this, and then salted meat like jerky and things kind of also use the same process in order of staying fresh, is because they're going to be so dry and then they're going to have typically salt on them as well. So any bacteria is then going to be in kind of this reverse situation because the meat itself is going to have the higher concentration of salt, lower concentration of water. So we're going to see the water is going to move out of the bacteria. Ultimately, they're just going to die because of that. So it helps keep the beef jerky and things fresh longer. But with these questions here, I'm just going to skip through them for now, just because I'm on my laptop, and then I'm going to look at the last section, and then I'll record a separate video on my tablet, so it's a little bit easier to kind of work through these different questions and see how to kind of set them up and things. But the last piece here is just going to be looking at colloids, and these are going to be kind of a middle ground, sort of, between solutions, which are going to be homogeneous, and then just heterogeneous mixtures, which are going to be uneven distributed. And with this, we can see a few just examples depending on what the solute and the solvent are going to be in terms of the different phases of matter. And actually, looking at this table, these two should be switched. Not what we actually have here, but the solute-like and the solvent-like pieces should be switched. Because the dispersing substance is essentially kind of the substance that's sort of doing the dissolving almost. In this case, we don't actually have it dissolving, but we can kind of think of it in terms of a solution. So that would be the solvent-like, and then the dispersed, the thing that's sort of mixed throughout, would then be the solute-like. So these two parentheses should be switched. But the term itself, dispersed or dispersing, is fine as it is. And then these different examples make sense because if we think about whipped cream, for example, the cream, the liquid, is going to be that dispersing substance. It's going to be kind of more like the solvent. But then we're going to have gas infused throughout it. And that's what gives it sort of that airy texture to it. And then milk is actually going to be an example. There's going to be globules of fat and protein that are essentially going to be suspended. And then with these colloids, that's what we're going to see. We won't have these substances dissolved, but they're also going to be so small that they're not going to settle out due to gravity. So we're just going to kind of have a mixed throughout. A couple other examples is just fog. So we've got the liquid water dispersed through the gas, kind of giving us the clouds. Smoke is a similar idea. It's just in that case, instead of the liquid, we're going to have the solid sort of soot particles floating in the air. And then you can see just a few other examples as well. So the marshmallow kind of similar to the whipped cream, just in this case, we're going to have a solid rather than the liquid cream itself. So that's why with the marshmallows, if you've ever placed them in one of the plastic syringes and just put your finger over the tip and then pull and push the syringe itself, you can see the marshmallow expand and compress just because there's going to be a lot of gas. At least you can do it a couple times before it kind of runs out. But it's going to be because there's actually gas within the marshmallow itself. And then a unique property of these colloids, especially in comparison to the typical solutions, is just going to be the effect that they have on light. So with the solutions, if we think back to one of the labs we did, a couple of the labs we did actually, we measured the absorbance, excuse me, of those solutions. And with that, we could pass light through, and then it just basically went through the other side because those substances were dissolved in solution. In this case, though, because we've got the particles just suspended, what we're going to see is the light's going to be scattered. And this is just known as the Tyndall Effect. And this is partly the reason why the sky looks blue, just because some wavelengths are going to be scattered more than others. And then also the reason we start to see sunsets is just because as the sun starts to set, the light itself passes through a different amount of the atmosphere. So we just get more of this effect occurring at different times. And that's why in some cases we've got the blue sky. In some cases we've got kind of the sunset colors where we're seeing here. In the case of the sunset, as the sun's getting lower in the sky, it actually passes through more of the atmosphere. So the blue light from the sun is scattered even more, allowing for like the red and the yellow to kind of be seen more compared to sort of the midday, where it'll pass through less of the sky. We have less of the blue light scattering there, and that's why we see the sky is blue. But with these colloids, we're going to see that they do have certain applications in terms of biological processes. And then with them, what we're going to see is certain molecules actually have kind of distinct pieces to it. So it may have a hydrophilic head, meaning that end of the molecule is going to be polar, it's going to be attracted to water. And then it may have a hydrophobic or lipophilic. So hydrophobic means water hating, lipophilic means fat loving. So they're going to be kind of the same idea in the sense that the non-polar is going to be kind of a characteristic of each of those. And then one of these substances, and I said the hydrophilic head before, because we've got in the case of something like sodium stearate, so we've got a sodium ion, and then we've got this negative carboxylate ion, excuse me. So we've got a carbon, double bonded oxygen, single bonded oxygen that's got a negative charge. That's why we have the attraction between the negative oxygen and the positive sodium here. So this portion of the molecule is going to be a polar component, so it's going to be attracted to water. But then we have this long carbon chain that's just filled in with hydrogens. So we've got this long section of the molecule that's going to be considered nonpolar. And then because of that, this can act as an emulsifying agent, meaning that it's going to essentially kind of allow two different immiscible liquids to kind of come together in some sense. So when we look at something like this, we've got a oil droplet. So you can kind of think of this as oil, as fat, something that's not going to mix with water. And then we've got it in we have it in water. So we can see the way that the sodium stearate is going to kind of interact is so that the non-polar carbon chain is going to be in the oil, whereas the polar head is going to be in the water. And this is going to be a stabilizing interaction. And something like this actually occurs throughout the digestive tract. So the gallbladder, excuse me, releases bile, and then that bile is going to contain structures like the sodium stearate we see here. And then because it's got those two heads, it's allowed to kind of interact with two different immiscible substances. And this is going to be important in terms of the absorption of different like fat soluble vitamins and things like that. It allows the digestion to occur more smoothly throughout the digestive system. And then, like I said, with this, I'm going to go back and record a separate video where I kind of go through the different practice problems here related to the colligative properties.